Salam sejahtera and a very good day to Dr. Habibullah. Our group project title is Optimization for Function with Several Variables. My name is Woon Kersin, and here's my teammates Tang Chun Yim, Xia Zhihong, Kao Yuanling, and Muhammad Alif Akmal bin Johari. The Lagrange multiplier is a strong mathematical tool that can be used in optimization to identify the local extrema of a function subject to equality requirements. This Lagrange multiplier method was inspired by Joseph Louis Lagrange, who lived in the 18th century. A composite function, also known as Lagrange, is created by adding Lagrange multiplier as extra parameters using the Lagrange multiplier methods. The premise that the object's function's gradient is parallel to the constraint's function's gradients at the optimal solution forms the conceptual basis of the Lagrange multiplier methods. This condition is easier to incorporate into the optimization process with the use of Lagrange multipliers. The optimization issue can be classified into two types based on whether the variable is continuous or discrete. Discrete optimization refers to an optimization issue involving discrete variables needs to be located from a countable set. A continuous optimization issue is one in which optimal values from a continuous function needs to be determined. It is a problem involving continuous variables. This can involve multimodal issues as well as restricted issues. The formula of optimization problem consider a generic optimization problem with the objective of either minimizing or maximizing an objective function under the constraint functions.
The key of concept is every decision maker wants maximize necessary thing and minimize the unnecessary thing. So the purpose of the study is determine the optimal value, which is maximum or minimum. So the main method will be used is Lagrange multiplier.
The primary aim of this study is to determine the optimal values of a multivariable functions, whether it is maximum or minimum within the parameters that have been clearly established. By applying Lagrange multiplier in a systematic manner, this work attempts to determine crucial points at which the objective function is simultaneously optimized and the constraints are satisfied. The overarching goal is to separate the complex interplay between the primary objective functions and its accompanying constraints. Through this analytical, the study aims to contribute to a better understanding of limited optimization methods with particular focus on the efficacy and usability of the Lagrange multiplier methods in the quest of optimal solutions in multivariable settings.
Today I will present the methodology for Lagrange multiplier. So first and foremost, we let the objective function become fxy and constraint function become gxy. Then how to find the value of x and y? Then we need to partial derivative fxy equal to lambda partial derivative gxy. Then we do some algebra expression, we can get the value of x and value of y. Then how to prove that the value of x and value of y, which is maximum or minimum? So we can use the substitution method. Then actually we use the substitute from gxy function to fxy function in order to allow fxy function become a single variable function. So we can find the first derivative of function fx or fy. Then in order to determine the critical value, after that we can also do the second derivative of function. If the second derivative of function fx is bigger than 0, which is x is minimum value, so we can conclude that y is minimum value. If the second derivative of the function fx is less than 0, which is x is maximum value, then we also can conclude that y is maximum value.
Lagrange multiplier are crucial mathematical tools in business and economics for optimizing resource allocation, cost minimization, profit maximization, and portfolio optimization in goal-constrained environments. They guide consumer choice and address environmental and social responsibility issues in corporate decision-making. Let us look at the example of business and economic application. Green Harvest Organic is a sustainable agriculture business that combines nature and innovation to cultural crops. The company is successfully relied on ecological process, capital investment, and a skilled workforce. The company faces the challenge of balancing crop yields with sustainable farming principle. With a budget of 10,000 ringgit Malaysia, the company is exploring the best value for eco-friendly capital and labor to increase crop yields while aligning with financial constraints. From our statement, we can know that the problem we need to solve is determining the value of eco-friendly capital K and labor L to maximize crop yields Q while staying within budget constraints, which is maximize Q equals to 4KL minus 2K power of 2 minus L power of 2 subject to the constraint K plus L equals to 10. This optimization problem can be solved using the Lagrange multiplier method. Lagrange functions are created by combining an adjective function and constraint, which is 4KL minus 2K power of 2 minus L power of 2 plus lambda in bracket K plus L minus 10. Next, determine the partial derivative of Lagrange with respect to K, L, and lambda and set them to 0, and which can get the first equation 4L minus 4K plus lambda equals to 0, and the second equation 4K minus 2L plus lambda equals to 0, and the third equation K plus L minus 10 equals to 0. To determine the critical point, we use equation 1 minus equation 2, which can get L equals to 8K over 6. After that, we substitute equation 4 into equation 3, which can get K equals to 30 over 7. Then, we can substitute it into any equation. We substitute into equation 3, we can get L equals to 40 over 7. Thus, we determine that critical point is 30 over 7 and 40 over 7. Now we use the substitution method to verify the critical point, relative minimum or maximum value. We can get K equals to 30 over 7 and L equals to 40 over 7 using this method. And we use the second derivative to prove the critical point is maximum or minimum value. We can get the both value is smaller than 0. Since the answer of Lagrange multiplier method and substitution method is same, while the second derivative in substitution method are smaller than 0, we can prove that the critical point 30 over 7 and 40 over 7 is maximum. And we substitute inside the equation Q equals to 4KL minus 2K power of 2 and minus L power of 2, we can get the Q equals to 200 over 7. In conclusion, crop yields has maximized at eco-friendly capital is 4,286 ringgit Malaysia and labor is 5,714 ringgit Malaysia. Finally, the crop yields are 28,571.429 kg.
Next, Lagrange multiplier method has a geometry application in the context of constraint optimization problems. The Lagrange multiplier approach includes finding sites where the goal function's level set is the tangent to the constraint surface. That includes finding sites where the goal function's level set is the tangent of the constraint surface. The objective is to describe the mathematical equation is del f equals to lambda del g. The del f and the del g represents the gradients of the objective function and the constraints respectively, and the lambda is the Lagrange multiplier. For the example of geometry application, we try to apply on determine the maximum pasture that need to fencing along the river to find the least amount of fencing. We got two equations, which is fxy equals to xy and gxy equals to 2x plus y minus 3250. And then we differentiate both to find y value. ddx xy equals to ddx lambda times 2x plus y minus 3250. And then it becomes y equals to 2 lambda. After that, we differentiate again to find x value, which is ddy xy equals to ddy lambda times 2x plus y minus 3250. It becomes x equals to lambda. Then make it equal y equals to 2x. Then sub 2x into the equation gxy, and then 2x plus 2x minus 3250 equals to 0. And then the 4x equals to 3250. Then the value of x is 812.5 square feet. Then sub into y equals to 2x, which got 1625 square feet. And then sub the x value and the y value into the fxy equals to xy to get the amount of fencing, maximum fencing pasture, which is 1,320,312.5 square feet. To prove the area maximum, we have to let gxy equals to 0 to become y equals to 3250 minus 2x, which is first equation. Then we sub first equation into fxy equals to xy to get 3250x minus 2x squared. Then we differentiate the equation to become f prime xy equals to 3250 minus 4x. Then we differentiate twice to determine whether it is maximum or minimum. And since the value is negative 4, then it is maximum. After that, we let f prime xy equals to 0 to find the maximum value for x as a second equation, which is x equals to 812.5 square feet. Then we do the same thing to find y value, which is equals to 0, which is x equals to 3250 minus y over 2 as a third equation. Then we sub third equation into fxy and become 1625y minus 1 over 2y squared. Then we differentiate it to become f prime xy equals to 1625 minus y. Then we let the second derivative to determine whether it is maximum or minimum. Since it is negative 1, then it is maximum value. After that, we let f prime xy equals to 0, which is it becomes y equals to 1625 square feet. The maximum areas are needed. Since the length and the height of the area are maximum, the x value and y value sub it into fxy equals to xy to get 1,320,312.5 square feet. Therefore, the maximum area for fencing a rectangular meadow on the bank of a river is 1,320,312.5 square feet.
As a conclusion, throughout the report, two applications of Lagrange multipliers have been discussed. We realize that Lagrange multipliers play a crucial role for solving difficult optimization problems in many fields, especially business and economics. It supports allocation of resources, cost minimization, profit maximization, and portfolio optimization. It also offers reliable answers for complicated economic problems by creating a strong framework for identifying a suitable equilibrium within particular limitations. Furthermore, the geometric application of the Lagrange method in constraint optimization problems provide additional versatility. Using this method, local maxima and minima are found. The key concept of tangency remains true even in situations when there are several constraints. The geometric solution to limited optimization problems can be understood through a systematic and logical framework provided by the Lagrange multiplier theorem. Overall, Lagrange multipliers have many uses, such as solving critical economic issues and providing geometrical understanding of optimization issues. This emphasizes how important they are to mathematical modeling and decision-making in a variety of fields. That's all from us. Thank you.